Okay. Good morning, everyone, and happy Monday. Hopefully you have a good week. Okay, so like always, let's start with recap so that we can continue where we left off last time. Today we don't have Sophia, she's out of town, but if you participate, please email her so that you get those participation points. Great, so let's start. So the linear sequence and length of a protein impacts. Wow, yay! Okay, I'm going to go with Ted in the back. What's that? Impact the primary structure. Ryan, what else? Okay, so the structure, what structure other than primary structure? Katie, right?
3D structure.
Yes.
Secondary structure.
Perfect. So the primary structure impact the primary sequence obviously is the linear sequence is the primary structure. It impacts the secondary structure, and secondary structure impact tertiary structure, and the structure impact functionality. Perfect. What is a peptide bond, Tiffany? Yeah, exactly. Which group with which group? Do you know? Monique? Yeah, so the carboxyl group of one amino acid to the amine group of the other. So, and it's a condensation reaction, so you lose one molecule of water with every peptide bond. How can a peptide bond be broken? Go ahead, what's your name?
Abby.
Abby, yeah?
Hydrolysis.
With what?
Acid or base.
Acid and base. Heating? With acid or base, yes. Alex? Proteases, yes. Proteases, or you have different specificity. They can be proteases with a very specific binding site, or they can be peptidases that are not specific. They will just hydrolyze peptide. Perfect. What is the role of hydrophobic residues in the folding of a protein? Go ahead. Exactly. And the water is? And the water is expelled from the protein structure. And what kind of bonds stabilize the secondary structure in this? Go ahead, Alyssa. Hydrogen bonds. So once the water is expelled, the residues will not bond via hydrogen bond with the water. They will start bonding with each other via hydrogen bond, stabilizing the secondary structure. How about the tertiary structure? What kind of molecular interactions, Emma? Disulfide linkages is one, Axel? Ionic interactions. What? Dipole. Walter? Van der Waals is the dipole, the same? Ionic. Were you going to say something else, Claire? Okay. Go ahead. Already said. That's the covalent. There's one more. Sven. Hydrophobic interactions. Great. All sorts of molecular interactions basically would stabilize the tertiary structure, but the bond that causes the most stability is which one? Disulfide linkages. It contains the most energy. Can you name any solvents that will disrupt hydrogen bonding? Breaks hydrogen bonding. That's a hard one, right? It's in that table. I told you it's a good summary table that talks about all the bonds and the disruption of the bonds. You can look it up. Go ahead, Ryan. Detergents like STS detergent or urea. Urea form strong hydrogen bond itself, so if it's present, it will break hydrogen bonding so that the residues will form hydrogen bonding with the urea. So how about hydrophobic interactions? Organic solvents, very good, because hydrophobic groups would want to interact with organic solvent. If you put the protein in an organic solvent, the hydrophobic residues are going to stop interacting with each other and start interacting with the solvent. Okay. And also, as the detergent will break hydrophobic bonding as well. Disulfide linkages, what would break them? Huh? Reducing agents, of course. So glutathione, mercaptoethanol, cysteine, sulfites. How about ionic interactions? What would break them? Go ahead, in the back. Salt solution. So if you add NaCl or ammonium sulfate, the positive ion will react with negative charges on the protein, and then the negative ions will react with the positive. So positive and negative, negative and positive, so that the residues will not interact with each other via ionic, so that will break the ionic interactions. Other than salt, there's one more thing that will break ions. Changing the pH. So increasing the pH or decreasing the pH way too much, you generate like charges, so there will be repulsion, breaking ionic interactions within the structure. Perfect. How does the free energy concept explain the folding of the protein? That's a tough one, but let's try to remember it together. So once the protein peptide or polypeptide is formed, do you have a lot of free energy? Yes. So you have a lot of free energy. And then what happens? Okay, Katie? It wants to go to the most stable form. So what starts happening to contain the free energy? Intramolecular bonding. Intra, that means within the molecule itself. So intramolecular interactions start to occur, bondings start to happen, free energy starts to be contained, and then the enthalpy, which is the contained energy, increases, and the entropy, which is the chaos, decreases. Perfect. So this basically sums up almost everything we talked about last time. And I think this was the last slide when we talked about quaternary structure, which is another form that the protein might take to stabilize if the tertiary structure was not stable on its own. So the protein can form quaternary structure. But mind you, not every protein requires quaternary structure to be stable. Some do, like the caseins in milk, or the hemoglobin in the blood, or the collagen, which is a structural protein. So some proteins require this quaternary structure, which is multiple polypeptides associate together via different interactions to form a stable quaternary structure. And we talked about, this was the last slide, talking about the fibrous structure versus a globular structure. So globular proteins tend to form globular structure of quaternary structure, whereas fibrous proteins that are mainly very hydrophilic proteins, so there are not a lot of hydrophobic residues that want to hide and coil on each other, so they're mostly hydrophilic. They want to be exposed to water, so they form these long strands because they're mostly hydrophilic. And then they're stabilized mostly by hydrogen bonding and disulfide linkages. So they will form this kind of structure. Okay. And we said this is function usually for fibrous proteins is structure. And then the function of globular proteins, in many cases they're enzymes. They do have other physiological functions or other functional properties that we'll talk about later. Okay. So the next thing I want to mention is proteins could be Homo proteins, meaning only made up of amino acid. There are no other groups. Or they can be phosphorylated, so they have a phosphorus group attached to it, such as in the alpha and beta casein. You have the serine and threonine. They can be phosphorylated via post-translational changes in the cell, producing a phosphorylated protein. Or they can be glycoprotein with a carbohydrate moiety attached, such as the kappa casein in milk. Again, this is a post-translational modification. And we talked about the structure of the casein micelle, how the phosphoproteins or phosphorylated protein stabilizes the outside of the micelle with those hair-like structures that are hydrophilic, very negatively charged, so they can form a stable quaternary structure, and that is actually that's the glycoprotein on the outside. The phosphorylated protein is in the inside. They form calcium bridges. So the phosphorylated protein form calcium bridges among each other, so they form this quaternary structure, and the kappa casein with the glycoprotein on the outside negatively charged, giving that micelle stability in an aqueous medium. So stable colloidal system in milk. Okay, and then there is the lipoprotein, where you have a lipid component associated with the protein, such as in egg yolk. There are a lot of different lipoproteins that makes the egg yolk a great emulsifier. Okay, the last thing I want to talk about protein structure is the net charge. So you know the protein carries different groups with different charges. So you have the amine groups and you have the carboxyl groups, and some amino acids are basic, other amino acids are acidic. So if we combine all the charges on the protein at a particular pH, then you get a net charge. And the net charge is what impacts solubility. Not the total charge, the net charge, because you have pluses cancel minuses, or minuses cancel pluses. So at the pi, or at the isoelectric point of a particular protein, and each protein has a different isoelectric point, you have a net charge of 0. So if you add up all the charges, all the pluses and all the minuses at that particular pH, you'll end up with 0. That's the least soluble. That's when the protein is least soluble, at its isoelectric point, because you don't have a net charge. As you change the pH, as you change it to, let's say, more basic, you start getting more negative charge, because then the groups start giving protons as you titrate with the base, with OH minus. So the protein starts giving protons, so the net charge becomes negative, and solubility enhances because you have more interactions with water. Same happens when you decrease the pH, titrate with an acid. You have more protons in the system, so the protein starts picking up protons. So the net charge becomes positive, and then also solubility enhances. So as you increase as you titrate with more acid and you start getting like charges, you start getting repulsion between the different proteins, therefore they become more soluble. So they won't attract each other anymore because they have like charges. And same happens at the other end, where they have negative charge as net charge. So the charges are impacted by pH, and also they're impacted by salt. Because when you add ions to the system, so ions will start interacting with the proteins as well, and that will impact charge. And we'll talk more about, remember, salting in and salting out. We'll talk about that later. Okay, let's do a simple exercise. I'm sure in organic chemistry it's more complex. There is a complex equation for determining net charge, but let's talk simplistically just to get the idea of a net charge. At close to neutral pH, what is the net charge of a polypeptide that have 5 residues of lysine, 4 residues of arginine, 6 residues of aspartic, and 7 residues of glutamic acid, and 11 residues of glycine? Calculate. Simple math. There's no magic in this equation, just simple. But you need to know is what would be the charge of these different residues at neutral pH. So give it a go. you go. What would be the charge of lysine at neutral pH? Would it carry a positive charge or a negative charge? Positive. So lysine will carry a positive charge. It's a basic amino acid. What about arginine? Is it basic or acidic? It's basic, so it will also carry a positive charge. What about aspartic acid, glutamic acid? So these are acidic, so they will carry negative charge. All right, what about glycine at close to neutral? What? I heard a whisper that is correct. Huh? No net charge. It doesn't carry charge. Glycine has an H for R group, so it has no extra charge. So it has an amine group and a carboxyl group cancel each other at neutral pH. So if we add them, 5 pluses, 4 pluses, that's 9 pluses, 6 and 7, that's 13 minuses, and no net charge on this one. So simplistic math, it would be a net negative 4 charge. Simple. Again, I'm making it simple just to get into the idea of what is a net charge. It's really based on what residues you have and what would be their charge at a particular pH. Then you would cancel some pluses and minuses, and the net difference would be your net charge. Okay, the last piece here in this topic is how do we quantify protein? So there's so many different ways to quantify protein, but the golden method that is used usually to determine protein for nutrition labeling purposes is the Kjeldahl, and you'll learn more about it in food analysis. But in brief here, if you're going to be if you're a food scientist. So you will learn about Kjeldahl in detail, but here just briefly, it's a method based on quantifying nitrogen. So it is a series of chemical interactions that will lead to identification of total nitrogen. And then you will determine the total protein based on the percent nitrogen in each type of protein you're analyzing. So you get the percent nitrogen and you multiply by a conversion factor based on the percent nitrogen in that protein. You get a percent protein. The average, usually nitrogen content of a protein is 16%. So in general, proteins have 16% nitrogen. But they might vary a little bit from one protein to another based on the composition of amino acids. So, but if we say it's 16, 100 over 16 is 6.25. And that's where that conversion factor is come from. So that if you have a food product and you don't know the protein sources, or it's a mixture of different proteins, you always use a 6.25. But if you know that it's wheat, for example, wheat has about 18% nitrogen. So it's high in nitrogen. So 100 over 18 will give you a lower conversion factor. Whereas milk protein has lower nitrogen content. So it's towards the lower end. So 100 over 15 will give you a larger conversion factor. So keep that in mind. So it is really based on the percent of nitrogen in the protein, and you convert it to concentration of protein. Another thing that is important to know is that Kjeldahl is a crude method of analysis. That means it determines protein based on total nitrogen, and not all nitrogen in food comes from protein. What other sources you know or components could contribute to nitrogen? Maybe I'm going to rely on the nutrition people, if there are any nutrition people in the room. Yeah, go ahead. I can't hear you. No? Okay, so some vitamins have nitrogen in them. Some vitamin B have nitrogen in them. So other nucleic acids, urea, have nitrogen in them. Free amino acids, which are not proteins, contribute to nitrogen. So there are other components in food will contribute to nitrogen, so we're almost always overestimating the total protein in food. But that's how it is, and that's why it's called crude protein content determination. Okay. Oh, this story. Have you heard of the melamine? Yeah, do you know how melamine passed detection coming into the US in pet food? That's how it was discovered originally, in pet food. Do you know how it passed detection? This is how it passed detection, because Kaldal is the main method for determining protein content. So they measured nitrogen and they came up with the protein content. What the companies did is they supplemented the pet food. Instead of putting enough gluten in there, gluten proteins in there, in the meal, they put melamine, which is a product, synthetic product that is a lot of nitrogen in that. So they put enough of it so that it will trick the Kaldal method, to that it will state that it has a certain amount of protein where it's not, because the nitrogen was converted to protein where it's not coming from protein, it's coming from melamine. And that's how it passed detection when it was brought into the US. So, I mean, Kaldal is a great method, but it won't detect adulteration at some time, and that was an adulteration case where Kaldal failed or caused a problem. Okay, good. So with that, we kind of talked about all of the intrinsic factors, or most of them, except for protein sources. We talked about the composition, the sequence, the different groups, hydrophobicity, structural conformation, and molecular interactions. So, and that leads to the native structure of protein, but usually we consume food processed. Okay, so processing impacts the structure. So now we're going to move on and talk about extrinsic factors, starting with heat processing or thermal processing of the food and how that would impact protein structure. So food is processed, and it's processed for so many different reasons. First of all, inactivation of enzymes, for example, that would prevent browning of food or prevent proteolysis or lipolysis in food. So heating inactivate enzyme, and of course, destruction of microorganism, food safety. So we process to pasteurize the food and sometimes sterilize the food. So we have to process. Also, development of flavor and texture. Who likes to eat raw meat? It doesn't taste good, even if it's safe and doesn't have microbes. It just doesn't taste good and doesn't feel good in your mouth. So you process to develop flavor and texture. Destruction of toxic compounds, like lectins, for example, in beans. So heating inactivate them. And improvement of nutritional quality oftentimes enhances digestibility. So for example, some proteins require partial denaturation, so they are when your protein is open up, digestive enzyme can reach binding sites and can hydrolyze the protein or digest the protein better. Also starch. Raw starch is not as digestible as gelatinized starch. So you can have more access to components for nutritional impact or nutritional value when the food is processed. However, processing have a direct impact on protein functionality. So some are desired, some are undesired. Let's list some desired ones. I already mentioned one. Yes. Aha. Yes, that's a very good one that I didn't talk about. Yes, structural changing when you impart processing, especially physical changes, and we'll talk about physical denaturation of the protein. It will impart formation of a gluten network. That's great. Another one. Yeah, go ahead. Yeah, it helps with protein digestibility. Partial denaturation helps with protein digestibility. Thermally induced gelation, right? So you heat collagen, you form gelatin, you get a jelly. So that is improvement in functionality. Sometimes you really need to denature the protein to have good emulsifying properties. So you heat the protein a little bit, you get better emulsification and better foaming. I think emulsification and foam, you will learn about it when you study colloidal systems. Did you talk about that yet? Colloidal systems? No? Okay, that should come at some point. Let's see, what do we have? Oh, undesired. Let's list some undesired. Excess heating or high temperature heating for elongated period of time. The protein will denature completely and polymerize, come together via intermolecular interaction, and we'll describe this in a minute here. And this causes the protein polymers to form. That means you will end up with large aggregates, and then they will be hard to digest. Also, heat treatment can inactivate desirable enzymes. Let me just show them. Okay, I don't know if you have this slide, but we did talk about these three. The one I didn't mention is a good one, is inhibition of or denaturation of trypsin inhibitor. We talked about trypsin inhibitor impacting trypsin digestion of our protein in the gut. So, and they're present in soy products. So soy products need to be thermally treated to inactivate 90% of the activity of trypsin inhibitor before consumption. So this is why processing is important in that case. Undesired insolubilization, like I said, when you denature the protein completely and the proteins start interacting with each other via intermolecular interaction, they become large polymers. Then they will fall out of solution. And not just that, large polymers are hard to digest. Digestive enzymes in our gut won't be able to get into some of the binding sites. So, and then sometimes inhibition of desired enzyme. Say milk is wanting to be used to prepare some cheese that will be aged over time. The thermal treatment is lower than the actual pasteurization of milk. So thermal treatment is about 60 degrees for some period of time. Why? Because they don't want to inhibit enzymes that are needed for aging of the cheese later on. Maillard reaction, I have it here in the middle because sometimes it is desired for this nice brown color of the bread, for example, and sometimes it's not desired. A beverage on the market, high protein and high fructose corn syrup, it will form Maillard reaction, and then you get browning, which is undesired. Okay. So let's have a look at what is protein denaturation. Change from its native form, okay, native structure, or in simple term, unfolding. Because often bonds are broken. When bonds are broken, the protein structure opens up. Okay, so that is what is called denaturation, going from in the natural form that is present to a different structure. So denaturation could start with loss of quaternary structure, if there is a quaternary structure, and then it could be loss of tertiary structure or change in the tertiary structure. Sometimes denaturation can also cause a change not only in the tertiary but in the secondary structure. And sometimes if there's hydrolysis, that would be change in the primary structure. So all of these are different steps of denaturation, but any change in the structure is a denaturation. It could be reversible or irreversible. So meaning you can denature the protein and it can go back to its native form, or you can denature it and then it takes a completely different form and it's irreversible. Okay. Short-term action. Okay. Let me explain this with an elastic. Okay. So I have an elastic in my hand. If I pull on this elastic for, say, 30 seconds and release, it's going to go back to its original shape. If I pull like that for 2 hours, I'm playing with it and I'm just pulling and pulling and pulling, will it go back to its original shape or will it be elongated? To be elongated. So that's what I mean for short term. So if you put the protein in an environment that results in denaturation, but a very short term, let's say reduce the pH quite a bit, you're going to change the ionization, but then if you bring it back to neutral, the protein reconfigures itself and reforms these bonds again. But if you keep it for a long time at this low pH or high pH, other things are going to happen. But also, if you heat it, and you heat the protein for a little bit and then remove it from heat, it will renature, denature, renature. But if you heat it in the presence of high concentration of protein, you put like 10% of protein in a solution and you heat it for high temperature long time, what's going to happen is the proteins start going to have intermolecular interaction. So let me restate. There's intramolecular and there's intermolecular. Intramolecular, that means within the protein itself. Intermolecular is with another polypeptide, with another protein. So in presence of high protein concentration and extended period of time of exposure to the denaturing agent, you'll end up, the protein will start polymerizing, either forming disulfide linkages or strong hydrophobic interactions. Because when the protein opens up, it's going to expose its hydrophobic residues to the water, and these hydrophobic residues hate water. It's like, I don't want to be exposed to water. So they're going to search for another entity that is hydrophobic. So another protein adjacent to it has their groups exposed, so they're going to come together and interact. So, and that's how polymerization occurs. And once strong interaction occurs, including disulfide linkages, this becomes irreversible. So think about a gelatin. If you put, I don't know if 3102 you did that. If you put gelatin and you heat it and then let it cool down, it will solidify into a gel. Heat it again, it will become a solution again. However, cook an egg. The egg white becomes a solid egg white, right? But when you cool it, it's solid. Heat it again, it's still solid. It won't go back. It's irreversible because egg protein is high in sulfur. You're going to form a lot of disulfide bonds and a very strong hydrophobic interaction. Cannot solubilize an egg white once it's formed, which is right here. So there's a jelly and then an egg white. A gelatin-based jelly could be resolubilized, whereas an egg white cannot. So denaturation temperature is unique for every protein. So different proteins with different structure denature at different temperatures. Okay, here's an example. Casein is stable at 140 degrees C, very thermally stable protein, whereas whey protein denatures at temperature greater than 73 degrees C, at or greater. Why is that? I'll tell you. Simply, it has to do with the structure. Whey proteins are globular proteins, have a lot of their residues inside of the globular moiety, whereas casein is an open structure protein. It's very amphiphilic. It has hydrophobic pouches and hydrophilic pouches in an open structure. So globular proteins are more sensitive to heat and they have secondary structure. Casein has a random coil for a structure. So the secondary structure, beta sheet and alpha helix, are very susceptible to thermal denaturation. They break up. the hydrogen bonding break up. The hydrogen bonding is destabilized by heating. Hydrogen bonding, van der Waals, electrostatic decrease as temperature increases. So they're destabilized by heating. The protein structure opens up. So a globular protein has a lower denaturation temperature, or temperature at which you get a structural change. That's what denaturation temperature is. Okay, so as you heat, you have you reduce the interactions within the molecule in the hydrogen bonding, van der Waals, electrostatic. However, hydrophobic interaction increases up to a certain point, and then it weakens again. And then if you have disulfide bonds in a protein, you would need more heat to denature it than another protein that has no disulfide linkages. So if you're looking, again, the example I gave last time, beta-lactoglobulin versus albumin in whey protein. Albumin is mostly, it doesn't have disulfide linkages, so it requires less temperature to denature, or lower temperature to denature. Water plays an important role in denaturation. If you have dry powder of protein, it's in a static situation. So it's in a static condition. That means there's no movement. There's no lot of movement. So you need a really high temperature to denature the protein. So here's an illustration figure. This is temperature here on the y-axis, and this is water content on the x-axis, and on the other y-axis here you have change in enthalpy, which is change in the contained energy. So look at here, when you have water, 2 grams per gram of protein, or very low water, relatively low water, you have really high denaturation temperature. As you start increasing the water, you can see even you go from 0 to 0.35 grams. So you start seeing a decrease in denaturation temperature. And then you can see a tremendous change in enthalpy. A lot of bonds are broken in the presence of water. So why is that? So hydration. So the water penetrates. When you heat, you have more kinetic energy, so you have movement. As you heat and there's water, the water starts moving, and the water starts getting into the protein structure, causes swelling. And then what happens? When water enters the moiety of the protein, what happens? Think about bonds. Water is inside now. Which bonds will be broken? Yes, right? Hydrogen bonds. So the hydrogen bonds will be broken, and then the residues will start interacting with the water molecules, forming hydrogen bonds. So swelling occurs because water goes in and the protein structure starts opening up and interacting with water. That's why with heat and water you get more denaturation than when you have dry powder and heat. Okay. Other denaturing agents, so like charges. When you create like charges, then you are breaking ionic interactions. So you will start having intramolecular repulsion. So when all the charges are positive, like at low pH, or all the charges are negative, you have a negative charge at high pH, the protein structure starts to open up because there's repulsion within the protein. So that causes denaturation. So, and then again swelling because of water starting going into the structure of the protein once the protein starts to open up. Let's say loss of complete surface charge. That means at isoelectric point. So remember at the beginning of the first lecture, I gave you the example of milk and yogurt. So yogurt is basically formed when the pH drops to the isoelectric point of casein. So when you drop during fermentation of milk to form the yogurt, the pH reaches pI 4.6, which is the isoelectric point of casein. At that point, you lose net charge on the surface. Because you lost net charge on the surface, the proteins start coming together. No more repulsion between these casein micelles, so they start coming together and forming the gel, the three-dimensional gel. Now, if you drop the pH to the isoelectric point for a short period of time and then neutralize again, you're going to solubilize that yogurt. But if you leave it, it's going to settle and more strong hydrophobic bonding is going to occur, calcium phosphate bridge is going to occur, then they won't be solubilized again. Again, short term, you can reverse it. Long term, it's done. Expose it also to very low pH or very high pH. For an extended period of time, you get partial hydrolysis of the peptide bonds. You get deamidation of asparagine and glutamine. They become aspartic acid and glutamic acid. You get destruction of sulfidyl groups at alkaline pH. And then the destruction of sulfidyl groups, meaning sulfidyl groups will get oxidized, and they form disulfide linkages, get aggregation, it becomes irreversible denaturation. Okay. You can interrupt me with questions if you'd like me to repeat anything. Okay. Salt. I mentioned salting in and salting out, so let's talk about a little bit. So the impact of ions in the solution. The phenomena salting in is usually used in beverages, high protein beverages. You want to keep the proteins in solution, so they add a little bit of salt. So here you can see magnesium phosphate, citrate, sodium ascorbate, sodium chloride. All of these are added to stabilize the protein. So when you add certain types of salts, they actually bind weakly to the protein and enhance the charge load on the protein. So in solution of low ionic strength, you are really increasing the charge on the protein, and again at low concentration of the ion, and then you will have enhanced water interaction with the protein and reduced denaturation. When you have a lot of charge on the surrounding the protein, it will reduce opening up because the hydrophobic groups don't want to be exposed to charges. Okay? So the protein resists unfolding, and they will have higher denaturation temperature in the presence of salt. So they will be more stable for a certain concentration. However, I mean, there is a salting out. If you add a specific type of salt at a certain concentration, that salt will bind strongly. So we have salt that enhance hydration and bind weakly, and we have different types of salt, like the ammonium sulfate, for example, bind strongly to the protein at a high concentration and neutralizes charges or shield charges. So you will have net zero charge on the surface. So they won't interact as much with water, and high concentration of salt competes for water. So the salt starts competing for water interaction, then there won't be enough water to interact with the protein. Proteins will fall out of solution. So this happens really at high concentrations for specific types of salt that you use specifically to salt out, and it's used for protein separation. Salting out is a common procedure to precipitate protein and purify protein from a matrix. Okay. Organic solvents, we did say that proteins in organic solvent, they will denature. Why? Because now there's no water, so the organic solvent will promote those residues, hydrophobic residues in the inside, to start wanting to interact with the solvent now because the solvent is suitable for them, is nonpolar and suitable for these hydrophobic residues. So the proteins opened up and hydrophobic groups are exposed, and that results in aggregation. So hydrophobic groups start interacting with other hydrophobic groups adjacent to them and from a different polypeptide, and they form a big aggregate and they precipitate. Reducing agents and organic solutes and detergents. So if you have a protein that is stabilized by disulfide linkages, add a reducing agent like glutathione or mercaptoethanol, it will break the linkages and the structure opens up. Sometimes this is useful in analytical methods. Sometimes the protein is a composite protein or quaternary structure protein, very large, different peptides. And you want to see individual subunits. You want to understand and characterize individual subunits. So you add a reducing agent and you break it up so you can study individual units. So sometimes this is done in an analytical setting. Okay, urea and sodium didosyl sulfide. This is a detergent. Sodium didosyl sulfide is a detergent. It's a powerful denaturant, and it breaks hydrogen bonding, ionic, hydrophobic van der Waals. It breaks, detergent breaks, or hydrophobic as well. Detergent breaks every type of non-covalent bonding. Urea specifically breaks hydrogen bonding because it can form strong hydrogen bonding with residues. And it destructures the water around the protein. You know, the water forms a certain structure around the protein. Presence of urea disrupts hydrogen bonding of the protein with the water and with internal hydrogen bonding within the molecule itself. There's physical denaturation. So this is a perfect example of forming a dough. When you knead the dough, you are denaturing the proteins or the gluten-forming proteins, gliadin and glutenins. You're opening them up and bringing them in close proximity to each other to form the gluten network. So that's a physical denaturation. Beating of the egg. So when you beat, you generate the foam. The protein also is denatured by beating the protein. And then what happens, here's what happens. When you knead, you form the gluten strands, inducing disulfide linkages and hydrogen bonding. Whereas when you beat and incorporate air, the protein unfolds. The hydrophilic faces the aqueous, and the hydrophobic component of the protein faces the air, and then you form the air bubbles and the film around each air bubble. When your film is formed, hydrophilic residues of that protein in the film around the bubble is exposed to the water, and then the hydrophobic residues are exposed to the air, and your bubbles are stabilized by a film, a protein film around the bubble. Enzymes, that's the last thing I'm going to talk about before I let you go. Enzymes will hydrolyze the protein. So again, denaturation of the primary structure by breaking peptide bonds. A perfect example is the formation of the curd, the rennet curd, or when the milk, you put an enzyme, chymosin, and then what happens, it disrupts the quaternary structure of the micelle. Chymosin is going to break off the glycomacropeptide, we call it, because that's the glycosylated peptide of the kappa casein. So it's going to break it off, and when it breaks it off, that negatively charged peptide is broken off. So the whole micelle is destabilized because you don't have that repulsion of the net negative charge between the micelles. So they're going to start coming together because there's no net charge anymore. They're going to come, fuse, form hydrophobic bonding and calcium phosphate bridges. and then you end up with an irreversible curd that is formed. I'm going to stop here. We're going to start there next time, and next time on Wednesday will be the last lecture.